let's see, I want you to be aware of your first homework assignment is due a week from today. So you've got a little bit less than a week because it's due at 9:30 a.m. You have to upload it to MU Online. Next week, though, your lectures will be delivered electronically. We won't have any in-person meetings Tuesday or Thursday of next week. And so we'll cover the material you need for that assignment during today's lecture and on Thursday. But you'll be submitting it electronically, and then that day's lecture is also online. In order for us to make good progress, what you need to do is next class period, download and install the HY8 software. That program is made available. It's publicly available. I think it's the Army Corps of Engineers. Or no, maybe it's Federal Highways. Federal Highways, all right. So it's available as a download. It's pretty small. It only works on PC, though. It doesn't work on Mac, unless you've got, you know, like a PC emulator boot camp or whatever. So today we're going to be talking about flumes and culverts. Any questions before we get into that? No? All right. Well, let's just briefly review. Way back last semester we had a lecture where we were talking about weirs. And one of the tools that's available for measuring flow rate is a broad-crested weir. And the idea of the broad-crested weir, if you remember in specific energy, when we have an obstruction in the channel, if we make the obstruction tall enough, then the water is forced to flow at a critical depth over the obstruction, because that's the most efficient flow rate with the lowest energy requirements to get a certain volume of water within a certain period of time over the obstruction. So remember, if we have pooling upstream, the water level is rising until enough specific energy accumulates upstream so that it can get its way over the obstruction. So we have some device that we know is going to cause critical flow over the obstruction, and then we can use that measured depth of critical flow there to identify what's the flow rate. And so if we know the critical depth there, we know that the critical depth represents 2/3 of the total head, because 1/3 of the head will exist as velocity head, the other 2/3 will be just the depth of the flow. And so we can use a broad-crested weir to identify the flow rate. And of course, there's some coefficient of discharge here that is related to edge effects and turbulence and energy loss. You know, you don't have a perfect you don't have a perfect transfer of the energy upstream of a broad-crested weir to the section right at the weir itself, and so we have to have this C sub D factor to account for the amount of energy that's lost. B was the width of the weir, and so last semester we talked about broad-crested weir. And so we've already discussed, reviewed, they work by inducing critical flow, but does anybody remember, I think we talked about this briefly, some of the disadvantages of a broad-crested weir? That's exactly right. It traps sediment and trash. And so you think about, if you have this upstream face here, this would be a perfect location for just soil particles to settle down, rock, debris, especially if you have varying flow rates, where sometimes the flow rate is fast and sometimes the flow rate is slow. When you have fast-moving water, then heavy particles can be suspended. Like big boulders can be moved during periods of fast-moving water. But then as the flow rate decreases, the particles that are heavier start to settle down, and only fine particles can continue to be entrained in slower-moving water. And so during periods of low flow rate, then trash and sediment can accumulate here, and then that can cause further energy losses, and it can interfere with our ability to measure the critical flow there. So that's one of the disadvantages, is that just operationally it requires a lot of maintenance. And then the other is that there's more energy loss than we'd like. You know, it's an obstruction that causes pooling upstream. And so we're causing an effect that works its way upstream of increasing the depth, and that may mean that a water conveyance channel has to be deeper than it otherwise would have been if we didn't have this obstruction in the way. So we would prefer to have something that didn't obstruct the flow. So let's do a compare and contrast here briefly. On the left is a weir, which we've just been talking about. And in the weir, what we do is we raise the bottom in order to force critical flow through a certain section that we measure the depth. And there's a lot of head loss, sediment deposition. And the main reason why we do it in the first place is just to find out what's the flow rate in open channel. In a pipe, it's a little bit easier to measure the flow rate because there are a lot of like magnetometers and pressure differential that can be used to quantify the flow rate. But in open channels, it's a little bit more tricky because you don't have a pressurized conduit that you can apply an instrument to. Now, in contrast to a weir, which causes the critical flow by raising the bottom of the channel, what a flume does is it causes contraction through some combination of changing the bottom elevation, but then also restricting the width. And a contraction is nearly as effective as an obstruction where you're going to be able to induce critical conditions, but able to avoid the sediment deposition. And we'll look at a cross-sectional view in just a moment. From this view, it's not immediately obvious why you wouldn't have sediment deposition. But basically, you're making the channel narrower, but you're not putting in a big step up that the water has to go over. Another advantage is the reduced head loss, and there's a brief video there. I think we probably do have time to watch that, so let's take a look at this video. Get the sound figured out though. No, try the TV.
The American Society of Agricultural and Biological Engineers' 19th historic landmark designation is the partial measuring flume. Since the beginning of irrigated agriculture, it has been important to accurately control and measure flows of irrigation water. Ralph Leroy Partial was born in Golden, Colorado in 1881. After high school, he enrolled at Colorado Agricultural College in Fort Collins, now Colorado State University, and received a Bachelor of Science degree in Civil and Irrigation Engineering in 1904. In 1915, Partial joined the USDA as an irrigation engineer stationed in Fort Collins. In March 1928, he reported on an improved Venturi flume. It was unique, most importantly, by having an oppression in the floor of the throat section. It required fewer stage readings to determine discharge and improved accuracy. In the days before pocket calculators and computers, Partial's statement that the flow equations for the flume are not particularly complicated, they can be readily solved by means of logarithms, was very important. This wooden flume, installed in an irrigation canal near Rocky Ford, Colorado in 1924, may represent the first working installation. In December 1929, the Irrigation Hydraulics Committee of the American Society of Civil Engineers unanimously resolved that the flume should be named the partial measuring flume. Partial measuring flumes have been designed and calibrated in a wide range of sizes. A partial measuring flume with a 1-inch throat can measure flows as low as 2 gallons per minute. This 30-foot flume operates in a canal in northern Colorado. A partial measuring flume with a 50-foot throat width has a capacity of more than 3,000 cubic feet per second. Partial measuring flumes have been constructed from wood, concrete blocks, poured-in-place concrete, steel and aluminum sheets, and fiberglass. They are being used worldwide, not only for irrigation flow measurement, but for industrial processes, municipal water supply, and wastewater treatment. This plaque commemorating the partial measuring flume was dedicated in 1985 and can be seen at the northeast corner of the Lowry Student Center on the Colorado State University campus in Fort Collins, the former site of the hydraulics laboratory where Partial conducted much of his research.
All right, so there's some interesting information in there. It talks more about the advantages, and it said that one of the big advantages in those olden days was the computational ease of using a partial flume. Here's a side view that maybe helps to illustrate a little bit more, and of course you got to see him in the video there. One of the really powerful things about them is the wide range of flow rates that can be quantified. Usually when you have instruments, especially for flow rate measuring, it's just over a pretty narrow band of flow rates that they'd be effective and accurate. But the partial flume is kind of unique in that you could have a really low flow rate and a much higher flow rate could also be measured in the same flume just as the depth increases. And so here you have the water is approaching from this direction. You can see the flow is indicated with the arrow. And the water enters this narrowing channel here, and as it gets towards the throat, the width of the channel is contracting, and that's the contraction in addition to a decrease in the elevation, sort of like an abrupt drop inside of the throat, induces the critical conditions that you can measure the two depths, and then there are empirical equations that you can substitute the two depth measurements into in order to get the flow rate. So here's a top view that's showing the converging section where the width is decreasing, the throat, and a lot of the equations that we use for measuring the flow rate are based on a certain throat width. And so there will be different empirical equations, say for a 1 foot throat width, a 1.5 foot throat width, and so on. And you can make adjustments. If you don't have a specific equation for the throat width that you need, there are ways to scale the flow rate up or down. But you would measure the depth of flow in the converging section, measure the depth of flow in the throat, and then the empirical equations are based on those two depths along with the width of the throat itself. So here are a couple of equations that are found in your textbook, and you'll notice that on the left side here it's saying for a certain flow rate, a certain throat width, which equation you'd use. Now some of them don't actually use the h sub b directly in the equation, but what you need to know, the difference between the upstream depth and the downstream depth, you sometimes need to assess whether or not the hydraulic jump that's formed in a partial flume is submerged. You remember when we were playing with the flume back in the lab that if you move the hydraulic jump really close to the gate, that the hydraulic jump kind of disappeared. Like the flow in the tailwater, the depth was increasing, and it actually drowned the hydraulic jump. The hydraulic jump was still there, it's just it wasn't freely visible. And so there's part of the procedure of using these equations is to find out whether the hydraulic jump is drowned and according to the ratio of the upstream and the downstream depth, and then we apply a correction factor if it is. So you would basically find the equation that you're using based on a certain throat width, and then plug in the upstream depth in the converging section to know what's the free flow capacity. We'll go through an example in a minute. The exact calculation process is more clear when we actually try out an example. So you have to find out the maximum depth that the depth in the throat can be in order to avoid the submergence of the hydraulic jump. And so here's the ratio of HB to HA. And again, HB is the depth in the throat. HA is the depth at a certain point in the converging section. And so if you have the ratio more than 50%, then it would be considered submerged, and then you'd have to apply a correction factor in addition to this equation. Here's how the correction factor works: is you'd find out the upper head and then the percent submergence, the ratio of those two, and then so you'd go over from the left to whatever percentage factor there is, and then down, and then that would tell you the correction that you have to subtract from the free flow rate that would come from an equation table like this. And so having the hydraulic jump drowned inside of the throat decreases the capacity. It doesn't increase the capacity. So you'd always subtract the correction that has to be applied. And sometimes this table, for example, is for a throat width of 0.3 meters. But if you may have a table like this for the throat width that you need. You know, if you're going to be building a partial flume that's 0.46, then you could get a table specifically for 0.46, or you can use the correction figure from another width along with a correction factor. So you can see here the 1.4. You could use a correction factor and then the table from a different width as a way of extrapolating if you don't have exactly the figure that you need. So just to illustrate that process from beginning to end, let's take a look at this example where we have a partial flume with a throat width of 0.61 meters. So in this figure, that would be the W, 0.61 meters. And then the depth in the converging section is 45 centimeters, or in other words, 0.45 meters. So the converging section is where we measure H sub A. And it says the depth in the throat is 0.39 meters. And the throat is where we measure H sub B. So what we want to know, first of all, is the hydraulic jump submerged? And so we have to look at the ratio of these two depths and the submergence criteria for a throat width of 0.61 meters. So if we go back to this table, we'll check the submergence criteria. And so the throat width is 0.61 meters, so that puts us here in this range. And so what is HB divided by HA? Has anybody calculated that ratio? So find HB, HA, and then compare that to the limit of 0.7 to find out whether it's submerged or not. Oh, good question. Yeah. The converging section is HA. HB is the throat. Anybody calculate that yet? HB to HA ratio? I think if we do 0.39 divided by 0.45, 0.867. All right. So that's larger than our threshold limit. So this limit said that the maximum HB to HA that you can have is 0.7 for it to be free-flowing. So the hydraulic jump inside of this flume isn't free-flowing, and so whatever flow rate we would calculate using the equation is actually going to be, the actual flow rate is lower. because our jump is submerged. So we just need to make a note of this, that it's submerged and we have to apply a correction factor. Now, in this example, we have a throat width of 0.61, and here I've provided the equation that you need. And the way you know which equation to use is just based on the throat width. And so for the throat width of 0.61, from this table, that tells us this is the equation. And so it's going to use the throat width as one variable, the depth in the converging section, h sub a, and then it's got also the throat width as an exponent, and then an exponent of the exponent. You don't see that every day. So the next step, you would calculate the flow rate if it was free-flowing. And so just put the given width and the given depth in the converging section into this equation, and you'll find some flow rate if it was free-flowing. And then once you've calculated that, we'll step through the correction process together. It's easy to make mistakes with this empirical equation just because of the exponent sort of thing. But I think if you put the numbers in correctly, what we end up with is that if it was free-flowing, so if it didn't have the submergence, which remember we know it does, we'll make that correction in just a moment. But if it didn't have submergence, then that flume would be carrying a capacity of 0.4151 cubic meters per second, based on how wide it is and what the depth is. Any questions about this so far? Okay, so the process is once you calculate the free flow capacity, now we have to apply the correction factor. And so this figure was actually developed for a different throat width than what we've got. This figure is the throat width of 0.30 meters. And so we're going to have to, if we want to use this figure, apply a correction factor of 1.8 to whatever we get from this figure. And so in the figure, what I did is I'm just illustrating our percent submergence. Let's see, just the upper head is 0.45. And so this scale is not linear, you'll note. And so finding exactly where 0.45 is a little bit of an art, as much as something absolute. But if it's 1, 2, 3, and it looks like from 1 to 3 you go maybe 3/5 of the way to the top to get to that. And so based on that, the rate at which it's changing, I said here is 0.45, and then we're going to go over until we intercept the percent submergence. And for us, our percent submergence is 86.7. That was the 0.39 to 0.45. So we go over to about, you'll notice here, it's between the 86 and the 88 curve is where I then go down. And then if we read where that is on the horizontal axis, I interpret that to be from the figure about 0.044. So let me show you on the screen here what I had in mind. So if it was free-flowing, then we'd have this 0.4151. And then the correction factor of 1.8 comes because I'm using a different figure. I'm using a throat width figure of 0.3, but I'm applying it to this problem where the throat width is 0.61. So I can do that if I apply the correction factor. It's just I have to multiply the correction factor by the correction. And so you figure what the correction is by looking it up off of the table. And so that says the delta Q is going to be 0.0792 cubic meters per second. So the free flow capacity minus the correction minus the delta Q then tells me actually what is the flow rate at this given time. If it was in the field and I took these measurements, how much water is going through that flume. Give you a moment to finish writing your notes.
What does that reduce the flow of the submergence?
Because there's more energy loss when the hydraulic jump is meeting some basically still water downstream. If the hydraulic jump was going through the jump and it encountered nothing downstream, then there would be less energy loss. And so you can think of this as actually additional energy loss in the flume that is there because basically the tailwater capacity is too low. And that's what's causing the jump to be drowned or submerged as it is that the channel downstream doesn't have sufficient capacity to convey all of the flow without drowning part of the jump. All right, so now you know a lot about partial flumes. Not a lot maybe, but enough to do the first homework assignment. Let me just show you that there are some questions, I think, related to flumes in the first assignment. If we go over here to course content, I think I've uploaded that assignment. I think MU Online maybe is running a little slow today. Because I'm clicking and nothing's happening. Course content. Yeah, homework 1. All right. So it's got a question related to the partial flume. And you'll need to go through that same workflow process of, I'm saying do this on a throat width of 0.4 in the 5 foot wide. Did I really mean feet? I'm going to have to double check whether I really meant. Oh, yeah, I did. I meant 5 foot wide. So you need to convert that to meters. Yeah, that's like curveball city. All right. So you'll be going through this process of, finding the right equation based on the throat width, assessing the submergence based on the depths that are measured here, and then because the throat width is in between correction factors, I give you the note that you'll have to interpolate the correction factor. So so you do have a question related to what we just went over, partial flume. Now the rest of this stuff, and here's a second question, a design question related to partial flumes for a certain flow rate. And one of the things that's on the table here is the typical capacities of certain flumes, like the range of flow rates that a certain throat width would be acceptable for. So you can get started on problems 1 and 2 of the assignment, and then the HY8 stuff, Culverts and HY8, we actually won't get to until next time in our lecture. Any other questions related to partial flumes?
So with acceptable flow rates, is that scouring and overtopping?
Good question. Yeah, no, those are more just sort of like typical flow rates. Let me go back to the table. You're talking about these free flow capacities. Those would be the capacities that you could usually expect without having the jump choked, and based on the typical height of water for a certain width of a channel. And so it's mostly related to keeping the hydraulic jump from becoming submerged. Okay. Culverts. How many of you worked or have worked at DOH before, so several of you have worked with DOH. Wow. 1, 2, 3, 4, 5, 6, 7, 8. 8 of you have worked with DOH. So you probably, if you've worked with DOH, you know what culverts are, and maybe even you do if you haven't. I've got a culvert at the bottom of my driveway that is just a maintenance nightmare because anytime there's a really big storm, it'll get cleaned out. But if there's just smaller storms, then sediment accumulates and weeds grow in there. And culverts are terrible except for the alternative is even worse, like having a big ditch at the bottom of your driveway that you have to drive over is worse than having a culvert that you have to maintain. The purpose of these is to pass water under a road where you've got flow rates a lot less than you'd maybe need to justify a bridge. Now, how much water can get through a culvert depends on a lot of factors like the diameter of the culvert, how long they are, the slope of the pipe. Essentially, it's an open channel under most conditions. And so the things that last semester we talked about, what's going to account for the capacity of a channel, the roughness, the slope, the width or the height of the channel, all those same things apply. But then there's also a little bit of nuance to the inlet configuration. And so here you can see there's some wing walls. Here you've got a pipe that's mitered. And so those can actually have a pretty significant effect on the capacity of a culvert to convey water because there are energy losses as the water goes from a channel into the culvert. It's a transition, especially when the water levels are high. So there are a lot of things that determine the flow capacity of a culvert. And there's a wide range of what culverts look like. This is a concrete box culvert that, it might as well be a bridge for all the structural effort that's going to go into designing and all the concrete that's going to be poured to make this box culvert a reality. But it's going to have a lot of capacity and the road can go straight over it without any additional fill needed on top. Here's another culvert that's just going over a natural channel. And so in some cases the culvert will pour down a new channel. In other cases they'll try not to disturb the natural channel if it seems like it's got some good stability already. Sometimes though there's a lot of scour inside of the culverts. And if you go here in Huntington, there are a couple of places that look a lot like this, box culverts, concrete box culverts with really heavily scoured bottoms. And if the scour undermines the culvert, then you can have a collapse of it, and then it can affect the roadway up above. But even if it doesn't collapse, having a scour of the material that's inside the culvert makes the hydraulics a lot more complicated to try and assess. The vast majority, if you're just looking in terms of numbers of culverts in West Virginia, are going to be pipe culverts like this, corrugated metal, maybe galvanized steel. And they have a pretty good lifespan if they're maintained correctly. You can have a metal pipe culvert like this last 50 years or maybe even longer under good circumstances. The way that they work is they develop strength as they actually begin to collapse just a little bit. When you load soil up above them, the pipe will begin to flex a little bit, and as it flexes, it will compress the soil underneath it, and then the soil resists its further deformation and develops some strength. And so, the whole point of them is just to convey water under the roads, and culverts are used because bridges are expensive, and they're for a lot lower flow rates. Now, the tricky part is knowing how big a culvert should be. Because, in engineering, you can always solve a problem by just making the thing really, really oversized. And if you have an enormously large culvert, then it's going to pass the amount of water that needs to go through there. But as I alluded to earlier, sometimes in hydrology, what you have to really understand is your tolerance for failure. How often is it okay for the water levels to exceed the capacity of that culvert to convey it? And so at the bottom of my driveway, I don't mind if that culvert fails once a year. If the water goes over my driveway once a year, then that's probably, I can wait a few minutes for the water levels to die down. But on an interstate, it may be the 100-year storm that you want to use as a design standard, because our threshold for the added risk that high water levels pose motorists at such a high speed, maybe that risk can't be accepted. So it may be that you know what a certain flow rate is based on a certain return period, and then you size the culvert based on that. There are actually several different conditions that determine the flow rate through a culvert. And if I just draw a We'll look at some cross sections next time in class when we start to do the HY8 stuff. But basically, the water level can be submerging the entrance, the outlet, both, or maybe just one of those. And then also the slope of the culvert can determine whether conditions inside of the culvert are supercritical or subcritical. So there are these different combinations of flow conditions that we have to assess to know what equation actually governs in determining the flow rate. And the inlet types are also pretty important for determining the capacity of a culvert. And when you're doing design, which of these inlet types to use partly depends on how it would affect the flow rate, but then it's also going to be related to the materials that are next to the culvert and trying to make sure that there isn't any scour on the inside of the pipe and so on. Let's leave it here for today, and let me revisit this announcement that I'd like you to come to class on Thursday with a laptop and have HY8 installed on the laptop. Is anybody not able to do that? Because if not, I might try and track down one of those awful tablet computers, you know, from the other building. But you'd be much better off just installing HY8 on your own laptop. So I will see you then. Thursday, we're going to have kind of like a computer day. Those are always fun. You can get started on the homework, and you can get started on learning your terminology. So let me know if you've got any questions, and I'll see you Thursday.